Good day, this is Bob from Test Equipment Chronicles with Bob. Today we're going to do another one of Are You Smarter Than an AI? And the AI system I have is ChatGPT. We're going to go ahead and we're going to look at a series of components here. And these are slide components, or ignition components in a PowerPoint slide. So we'll go ahead and get started. And the very first slide we're going to be looking at here is slide number 1. And so on the bottom of the slide we have a component. It looks like it rotates, and it rotates in this case a clockwise rotation. Now the part that's hooked to it, that's up on top, that's in close proximity, what exactly is that component? How does it work? So give me a complete rundown on that.
That top component is a variable reluctance sensor. As that notched wheel rotates, the sensor detects changes in magnetic field. Each notch passing by induces a voltage signal. The ECM uses these signals to determine engine speed and crankshaft position, critical for ignition timing.
Okay, for a bonus round on that particular image, any idea what the application is that came out of?
That configuration is classic to many older ignition systems, often seen in 1980s to early 1990s vehicles. For example, Ford's EDIS, Electronic Distributorless Ignition System, used reluctor wheels and VR sensors just like that.
Nope, you are incorrect on that. This component actually ends up being out of a Chrysler. This component actually was used from 1973 when Chrysler first rolled out their ignition system. And then, well, that was used way in somewhere into the 90s, and then eventually it went away as crank and cam designs and more Hall effects came about. So it had a very long life, and it was very problematic and reliable in the same thing. I hate to say both at the same time. I know one thing with the reluctor wheel, they had a terrible tendency to want to get magnetized, especially if people are in there tapping on the engine or tapping on the distributor. And then you would have some unusual conditions for misfire. That was one of the problems that was kind of interesting. You needed a non-metallic feeler gauge to work with on this one also, because that reluctor clearance was very critical to actually setting everything up. So there's a little bit of a rundown. Let's look at this next slide here, slide number 2. It's a large disc. It's got a whole series of small slots on it, and then it's got 6 slots. 5 are small, the 6th is large. What was that used for? What kind of ignition system was it used in, and what was the logic behind this versus that reluctor that we've seen prior?
That disc with multiple slits is an optical or photoreflector wheel. It was commonly used in optical distributor ignition systems, like Nissan's optical distributors or some early GM designs. The small slits often indicate crank angle or degrees, while a larger slit marks a reference point, such as cylinder number 1. This allowed for precise digital timing signals, improving accuracy and enabling early electronic fuel injection coordination.
That is correct. Any known problems with these, other than, of course, electronic problems, but any kind of engine environmental conditions that you're aware of?
One known issue was contamination. Oil vapor or moisture inside the distributor could cloud the optical sensor window, causing misfires or poor timing. Also, any mechanical wear or play in the distributor shaft could throw off alignment, affecting accuracy. Keeping the unit clean and sealed was vital.
Well, that oil mist is exactly it. That was actually a problem. If the engine would develop some crankcase pressure, specifically the PCV valve, that was actually, most of them would have a calibrated orifice, but that would plug up and start building up positive pressure in the crankcase, and or the engine gets excessive blow-by. This would really cause some havoc for misfire triggering, injector triggering problems. So you got that one. Let's move on to the next one, number 3. This one here, we're showing a reluctor wheel, and then it has, if you look at both the waveform and then a reluctor wheel, there is a spot where we have a double notch. What was that double notch used for?
That double notch is a key reference point for the engine control module. Typically, it marks a specific cylinder, often cylinder number 1. The ECM uses it to synchronize the ignition or injection timing sequence, ensuring the correct order of events.
Okay, you got that one right on the money. It was pretty involved. It was used an awful lot, and if you think about it, how else would you find number 1? I think the first I ever seen this was on the early General Motors on their DIS systems, so distributorless ignition systems. That was pre-coil unplug, post-distributor. Okay, let's go on to the next one here. This one here we have a you can see a cam and a crankshaft timing chain assembly, and then there is a sensor located on the top of the engine. What is that sensor and what is its purpose?
That sensor on top is a camshaft position sensor. Its purpose is to identify the exact position of the camshaft, which helps the ECM determine proper sequential fuel injection timing, and in some cases variable valve timing. It works in tandem with the crankshaft sensor to keep everything synchronized.
Bingo, you got that one. Let's go on to the next one. This one's a little more involved. And what I want to look at here is we have a tone wheel on the center part of the image. And then within that tone wheel, we have looks like a tooth that's missing. That's going to go down to a module, and that module it communicates with the EEC4 system. That's Ford's computer controlled system. And then it goes out, and I wanted you to tell me a couple things here. And this is all going to pertain to the right side of the image. How many cylinders this engine has, and then how does it work? That unique system there, it's post-distributor but pre-coil unplug. But explain how the spark plugs are fired.
This is a 6-cylinder system. The missing tooth on the wheel provides a reference point for crank position. The module is a Ford VDIS, electronic distributorless ignition system. It fires the spark plugs in pairs, one cylinder on compression and its paired cylinder on the exhaust stroke. It's called a waste spark system, where one coil fires 2 plugs simultaneously. This was a bridge between distributors and modern coil unplug systems.
Actually, this is where I cut my teeth in engineering, working on developing the distributorless ignition system. You got to think about engine analyzers, pretty easy. We had a coil, and we had a number 1 spark plug. We had spark plug wires, so you could get to number 1, and you could easily get to the coil. So using engine analyzers was relatively straightforward till this came along. How do you get a number 1? Because every time the engine comes around, you have an ignition pulse that takes place on number 1 spark plug wire. So even if you have your number 1 pickup hooked to that, how do you go about figuring out when that ignition is on compression or when it's on exhaust? You have an idea what it took to do that.
Distinguish compression from exhaust stroke with a waste spark system, you'd need an additional input, like a camshaft position sensor. That sensor identifies which stroke the engine is on, letting you know when cylinder 1 is on compression versus exhaust. Without that, you'd be guessing.
Well, guess what? That is not true. So we might have to brush up on a little bit of our engineering here. In this particular case, we actually looked at the amount of energy growing across that wire, or basically would say the burn line, to see if it was under pressure or not. It was a pretty good system, but it had some problems. You could probably identify the problem it had. If you had a problem with number 1 cylinder, say you had a burnt exhaust valve where you couldn't produce adequate compression pressure, so your ignition would look the same from one cycle to the next. But other than that, it actually worked pretty good. It was a tough system even for technicians to hook up to get that information. These were, I remember, an awful lot of them were shotgunned with simply throwing coils and modules on them. And that got to be pretty expensive and very ineffective because, again, you had a lot of components that could go bad. But that was how we went about it. Okay, let's go on to the next slide. Okay, this is a little bit odd. So we have a flex plate or ring gear on the back of an engine, and we have a sensor to it, and we have a bunch of odd-shaped notches on the flex plate. Quite different than you would find, with the tone rings we had looked at earlier. What are the notches? How does that work? Give me a rundown here.
Those irregular notches on a flex plate act similarly to a crankshaft position tone ring, but they're typically part of a flywheel or flex plate assembly. The pattern of missing or uneven teeth creates a unique signature. The sensor reads that pattern to determine crankshaft position and speed. The odd shape helps identify the engine's exact position.
Yeah, exactly. It was kind of a genericized answer. This one's off a Chrysler. Seen a lot of these. A little bit off track here, but it was off a 6-cylinder. But these had a lot of problem right where they had flex plate bolts to the crankshaft, where they would crack the flywheel or the flex plate and actually get slightly retarded, and you would get the oddest things. Misfires on only one cylinder initially, and chase that problem around, and the whole problem was a cracked but not any noise out of it, just simply cracked and slightly shifted flex plate. I remember the very first one I got involved with. I spent a lot of quality time with a couple other techs in a shop with a lap scope on it, and we kept saying the computer's got to be malfunctioning, but why? We just didn't want to replace the computer. It just seemed to be too odd a thing that's getting, and we chased noise and all that. Eventually, we wanted to go in and just verify, and I think we pulled a starter out on it. And in the process of looking at it, we said, "Hey, this something looks odd." It's almost like the thing was running a little in a now I'm calling it an elliptical orbit, but it was slightly out of line. And of course, that's how we discovered it. So it was a combination of electronics and good old diagnostics by going in and doing a visual. Okay, that's enough of that story. Let's move on to the next slide here. This one is not ignition related. This is engine performance related. This is just a genericized image of an intake manifold. Could be off of any vehicle. It's one I used in class for decades and decades, and I learned on. So it's an oldie but a goodie. But you see the image on the left and the image on the right. What is the difference between the two, and then what is the difference between the gauge positions?
The left image shows manifold vacuum measured at idle, high vacuum due to a closed throttle. The right image shows manifold vacuum at wide open throttle, low vacuum due to maximum airflow. The gauges reflect this: high vacuum reading at idle and near zero vacuum at wide open throttle. This difference is key for diagnosing engine load and performance.
Okay, very good. Yeah, this was how all the carbureted systems work, and you normally would have 3 different ports. You didn't see them necessarily, but they had their different purposes. The Venturi vacuum could only achieve a small amount. Wide open throttle, you might get to 1 or 2 inches of mercury. The ported vacuum tracked it dead nuts with the manifold vacuum, except you would see no vacuum when the throttle plate was closed, and then it would come on as you open the throttle plate up. So this was something that a technician had to understand how this worked, because on the early emission components, they relied an awful lot on ported vacuum, and then they would sometimes use Venturi vacuum as part of the signal process. So you got that one. Let's go on to the next one here. Okay, we have 2 waveforms. These are just 2 images put next to each other, and we're not going to worry about what they are. They're obviously square waves. But what is the difference between the image on the left, and I'm not talking about magnitude, just simply what is the difference, the way we're looking at it, between the image on the left and the image on the right?
The difference is in the pulse timing. The left waveform has evenly spaced pulses, uniform timing. The right waveform shows a skit or longer gap between pulses. This gap is often a missing tooth or reference mark. providing a unique position signal, like top dead center.
Okay, you saw that wrong. That one you actually missed. They are actually identical signals, just the magnitude is different. I intentionally did that to kind of fool around a little bit here. But if you take a look at the image on the left, we are referencing ground. So the scope is referencing ground. Where you can see the one on the right would be AC coupled or simply not referencing the base ground, the battery ground. This may be a floating ground system, but in this particular case, we're just simply AC coupling it. So that would be the difference. So it's strictly an instrument in the way it was hooked up. Let's move on to the next one. Okay, this is going to be just a basic electrical logic test. So we're just going to apply a little bit of logic to this. So we have our source, our battery. In the center of the image, we have our consumer. Make it anything you want. It could be a light bulb, a blower fan, you name it. It could be, if it's going to work off of a battery, that's what the component would be. Now we're going to go down and the switch, there's two switches. I'm going to say the bottom switch we closed. So if that went from an open switch to a closed switch, what would be the outcome of the consumer?
The bottom switch closes while the top switch remains open. The circuit is completed. Current will flow from the source to the consumer. As a result, the consumer, whether it's a light or motor, will activate and operate. In short, the consumer turns on.
Okay, now we're going to reverse it. So the bottom switch is left open and the top switch is closed. What is the likely outcome?
The bottom switch is open and the top switch is closed. The circuit is still incomplete. No current will flow. As a result, the consumer will remain off. In short, nothing happens to the consumer.
Well, you hit that one right on the head. That's actually one I know a lot of students failed. It's got a controller, so we don't know what the controller is doing. So your answer was correct. You could make this opposite argument. The most correct answer would be it's unknown because we don't know what's going on with the controller itself. So adequate answer. We'll move on to the next slide. Okay, first off, can you identify what this slide is?
This slide shows a waveform generated by a variable reluctance sensor, a sine wave signal. It's a classic analog output as a toothed wheel passes by, with voltage rising and falling based on tooth proximity.
I'm going to have to cut you off here. No, it is not. That's just a secondary ignition system waveform. So that's the ignition system as it would be viewed from the engine analyzer, any kind of a scope. So we can see, and the only area that I'm most interested in is the area to the left. You have the spike going up, that would be the amount of energy it takes to ionize across the gap of both the rotor in most cases and the spark plug. And then there's called the burn line, the amount of energy that it takes to maintain the spark across there. And then you have your coil oscillations when it no longer can generate enough energy to ionize the gap anymore. So that's what it is. So that is a normal. I'm going to identify this. This is a normal waveform. I'm going to go on to the next one, and I have a very similar question to ask. Okay, on this next one here, we're going to be focusing over on the left side, that part of the image. Can you tell me what could be going on with this, since we now know it's a secondary ignition?
This waveform, the initial spike looks normal, but the burn line shows instability. Notice the oscillations or ripples during the spark duration. This often indicates a lean mixture or weak ignition. Basically, the spark is unstable due to inconsistent combustion conditions. It's not a smooth, steady line like a healthy burn.
Okay, you nailed that one right out of the ballpark. Yes, exactly that. That would be a very lean, most often a very lean condition. Could be excessively wide gap and lean condition, but either way, that was a classic we looked at for decades and decades and decades. Okay, we're going to go on to the next one. This one's a little bit different. We could see that we're way up there. We got a little bit of dynamics. So go ahead and give me a rundown of what you think this could be.
This secondary ignition waveform shows a much higher initial spike and a very errated burn line. That suggests a secondary ignition problem, like a fouled spark plug, a bad plug wire, or a cracked distributor cap. It's struggling to maintain a stable spark and can cause misfires under load.
Well, unfortunately, sometimes you do this. That was a too genericized response. That ends up being something that has an excessive amount of resistance internally, like a burnt rotor, where the top, where the center button of the cap to the rotor, or the rotor lug, it lugs on the cap, and or the tip of the rotor was burned away. Or in some cases here, simply a spark plug that has got a physical opening, in other words, an arc over in the spark plug or the coil wire. They are all pretty much the same thing, but it's pre-spark plug itself. Because of the consistency coming across, you see some turbulence, but that turbulence is riding on top, but the bulk of the problem is going to be an internal, external resistance from the spark plug. With, again, I'll make an exception, there is a few applications, but most of the time that's what I found, and I've seen thousands, especially the HEI distributors, that when they came on in the 70s, wow, they were really common for this problem. Okay, next one, next slide. What is this showing? Again, it's a secondary ignition, but what is the problem?
This secondary ignition waveform shows a very short burn line. Essentially, the spark is being quenched too quickly. That typically indicates a rich mixture or excessive fuel. The spark is easily extinguished because there's too much fuel, preventing a long, stable burn.
No, you got that one wrong. This is simply an open spark plug wire. It's so large of a gap that we don't have any burn in the first place. It just simply goes up and you see the oscillations back and forth, and that's the energy being distinguished inside of the coil itself. So no, this would be, odds are, a complete misfire. Okay, let's move on to the next one here. I'm showing a waveform that is two steps. What kind of application would this be, and what is it called?
This stepped waveform is a typical digital square wave signal from a Hall effect sensor. It's commonly used for crank or cam position sensing. Each step indicates a tooth or window passing by, giving precise timing data.
Nope, got that one completely wrong. This is a current limiting waveform. So we're looking at the voltage component of it, and we get voltage gets turned on, pulls the line down, current flows through often a very low resistance, say an injector with maybe a 1 ohm resistance. Well, that won't last very long at 12 volts, and it will quickly cause a calamity. A lot of these actually, when I think back, a lot of them are actually down around 0.5 ohms. Okay, so then at that point when the current level is reached, then it reduces the amount of voltage in there, so a current limiting system, and it's called a peak hold design. Can you give me any feedback on your knowledge of peak hold designs?
Absolutely. Peak hold designs are common in electronic fuel injectors. The system hits a peak current to open the injector quickly, then drops to a lower holding current to keep it open without overheating. It's efficient, reduces heat, and allows faster injector response. The key is that initial peak ensures rapid actuation.
Okay, what is this waveform?
This is a classic alternating current sine wave signal. It's symmetrical, positive, and negative. In automotive contexts, you typically see this from a variable reluctance sensor, like an older crank or wheel speed sensor, producing an analog sine wave as teeth pass by. The frequency correlates with speed.
Okay, got that one. Okay, kind of a follow-up. What is this waveform?
This waveform is a higher frequency AC sine wave, just like the last, but the teeth or pulses are closer together. In automotive systems, this indicates a faster rotation or higher speed.
Nope,
The
actually
same
got
type of sensor.
that one is
just
wrong.
a-
That's wrong. This is actually out of an alternator, so it's the three-phase, not completely rectified, coming out of the alternator. So it's an unrectified alternator showing all three phases. Okay, we're going to move on to our completion. Now, I got a question for you, ChatGPT. You had no pre-knowledge of this. When I started this out, that was the first you've seen these images. Is that correct?
That's absolutely correct. I was analyzing them live as you described and shared them.
Okay, well that does it for today. Hopefully everybody got something out of that. This is just a different way of looking at things, and we're seeing how our competition of AI is. Is it competition? Is it a helping hand? I don't know. I'm not even going to get involved in that part. But it is a tool, and it's a tool that we can use. It can be used for good or bad. So I want you just to see the different things you can actually do with it and its strengths and weaknesses. I will be continuing putting these together in different subject areas. So I want to thank you very much for joining me today. I hope you learned something and have the most wonderful day.